Alright guys, if y'all would number your handouts, 2 of them are 23, and then the one with all the graphs on it is 24. Give me just a second to update attendance. 23. Ramiro. Okay, so last time I saw you guys, we finished up with section 4.4, which was, I don't know, in my opinion, more of the same stuff from sections 4.1, 4.2, and 4.3. And probably all that stuff should have gone on the first test, but having 4 sections on one test would have been a lot, so we cut it off after 3 and we'll move on. So the rest of Unit 2, sections 4.5 and 4.6, feel like a little bit of a change of pace because we're going to be looking at graphing now. So section 4.5, which we're going to spend a few classes on today, tomorrow, and next Tuesday before we get to your quiz on it. It's all about graphing sine and cosine, so we go real in depth on those two and do a lot of transformations. And then 4.6 we don't spend much time on because it's just the other 4 graphs but no transformation, so there's a lot less to those. So if you guys are not aware, when you take the ACT, you're supposed to get 4 trig questions every single time. 2 of those 4 are supposed to be, or traditionally have been SOHCAHTOA questions. So things that hopefully you could have answered after geometry, but of course it helps that we have reviewed SOHCAHTOA in here, so those should be a little more comfortable. But the other 2 trig questions you really only get if you take pre-calculus. One of those, now it's not always the same 2 things, but one of the other 2 trig questions on the ACT is usually stuff about sine and cosine graphs. So in fact tomorrow I've got a handout for you that has like 5 practice questions that came from ACT practice. So let's go ahead and dive into it. So on the front page here we're going to talk about what the sine and cosine graphs look like, but both of these are really considered parent functions. So after we see these a couple times, you'll see it's really in your interest to memorize what they look like so you don't have to go through this process every time. But let's say 6 months from now you can't remember which one's sine and which one's cosine because they do look similar. You can always just plug in any unit circle values that you would like and make a table. So for example, I know the sine at 0 is 0, and then I could plot that as a point. I know at pi over 2, sine is 1, so I could plot that as a point. Notice our x-axis is not 1, 2, 3, 4, it's in terms of pi, so you got to pay attention to that. The sine of pi would be 0, the sine of 3 pi over 2 is negative 1, and then 2 pi is coterminal to 0, so those would have the same values. I'm just picking angles that I can quickly find the value of from the unit circle that don't have weird decimals. You could do different points, you could do more points, but at the end of this, once you connect them, this is what's called one cycle. That shows the full pattern of the sine graph. and it just keeps repeating. So if I went further to the right, I would continue the same pattern. If I go further to the left, we need to continue the same pattern. So really, as we go through this worksheet today, you always need to be very careful with the first cycle, but then if you've got that down carefully and correctly, you can just kind of copy and paste this. So like notice it's at 0 at the start, end, and the middle. So over here, the start, end, and at the middle is going to be 0. And the middle of these two is 1, so in the middle of those two is 1. In the middle of these two is -1, so in the middle of those two is -1. So the pattern just continues. And you can go further to the left and you can go further to the right, so we probably should put arrows on our graph. But that is what the sine graph looks like. So once again, we're going to use this so much that really it's nice to know the sine looks kind of like a wave. It goes through the origin, going up like that. But if you need specific points, or if you feel unsure if you memorized it correctly, just throw in a couple unit circle values and plot those points like I did on the table. Alright, if I do the same thing with the cosine graph, and I just throw in a few unit circle values that I can do quickly, bless you, I know the cosine at 0 is 1, plot the point. I know at pi/2, cosine is 0. At pi, he's -1. At 3 pi/2, he's back to 0. And 2 pi is coterminal to 0, so it's going to have the same value again. Connect those. And here is one cycle of the cosine graph. So that is the full pattern of cosine. So he continues on forever to the left and forever to the right. So on the right, I could put a little arrow to show that it keeps going. But on the left, I really kind of need to copy and paste this graph over here. So you can see both these graphs look pretty similar. They have both have the same domain, they have the same range, but the thing that stands out to me that makes them noticeably different is sine goes up through the origin, whereas cosine does not go through the origin. It goes through a y-intercept of 1. But you can always plug in unit circle values to find a few exact points, and then that can make you feel a little better about your graph. Now, I will admit we don't get into applications very much here, but if you guys do continue on a path for a career in math or science, you need to understand that there's tons of stuff in nature that just are naturally look like waves. Sound comes in waves, light comes in waves, microwaves,
Water.
Not water. But that's a good guess.
The waves in the ocean.
Yeah, not quite. I mean, maybe. Maybe if you were trying to model the surface of the ocean, potentially. But there's lots and lots and lots of stuff that if you continue that in the science course someday, you want to measure those things, manipulate those things, calculate those things, it's going to be a sine or cosine graph. There was no functions you learned in Algebra 2 that had this kind of curvature. Along those lines, try to not make these look like V's. These are not supposed to be sharp. There's supposed to be some curvature to it. So try to show that curvature. Try not to make it so zigzaggy. Okay, any questions about how I came up with the sine or cosine graph before we start making some changes to these? Okay. So this isn't 100% necessary, but it does kind of just tie in a few things we've already talked about. So I just like to make that connection for you because it helps you overall. If you remember that sine is an odd function, number 4 has a typo. All odd functions have symmetry with respect to the origin. Just like x cubed. What it means to have symmetry with respect to the origin is that you could rotate your graph 180 degrees also known as just turning your paper upside down and it looks the same. So I can't do that with my digital paper up here, but if you were willing to turn your paper upside down, your sine graph before you turn it and after you turn it should look the same. That's a characteristic of an odd function. Whereas cosine is an even function, and even functions, just like x squared, always have symmetry with respect to the y-axis. So notice if you took the cosine graph and you flip that stuff over the y-axis, it would land on the other side. So if you know that about even and odd functions, and you still remember that sine is odd and cosine's even, it can help you remember which one is symmetric to the origin versus which one's symmetric to the y-axis. Okay, so now we're going to deep dive into all of the changes that we can make. And we're going to look at all the changes one at a time, and then at the end of this we'll look at one that it's on the harder side, but it kind of pulls all of it together at once. Alright, just so we don't have to keep flipping back and forth to see the parent functions, I just have us quickly regraph sine and cosine. These are the same things we just talked about, but again, I don't want you to have to flip your paper back and forth, so let's go ahead and do a quick little sketch of those. Okay, one change that we're going to make about these graphs is how often these patterns, how often a cycle repeats itself. And that distance is referred to, is called period. In a science course, you'd probably call that frequency, like how frequently these waves repeat themselves. So sometimes you have to get that out of an equation, and I'll tell you how to do that in number 8. But sometimes you have to get it out of a graph. So since we've got our two graphs here, we can just measure the period. If I start measuring at 0, just because that's an easy one, I have to go this far to see one full cycle, one full pattern of its whatever, and all the way to the right here is 2 pi. So if the distance to see one full cycle is 2 pi, that in mathematics is what we call period. Cosine, if I start at 0, I would have to go this far to see one full pattern of his cycle, and that distance is also 2 pi. But depending on what these represent, we may need them to repeat more often or less often. So how we are going to manipulate that is we are going to put a number next to x, a number being multiplied by x. The math term for that is coefficient. We're going to call that number b, and then there is a formula to compute period when you only have the function. That formula is this: 2 pi divided by b. So there's like 3 formulas in this section, all very basic ones, but you have to know them. To calculate period, 2 pi divided by b, where b is the coefficient of x. So if we know what sine looks like, we can also figure out what sine of 2x looks like. Because now b is 2, I can calculate his period by using this formula and plugging in 2 in for b. And what that does is it changes the period from 2 pi to 1 pi. So visually, it's got the same pattern of up, down, down, and back to where you started, but instead of it achieving that in 2 pi of space, it's going to achieve that in 1 pi of space. So it's going to go start at the origin, it's going to go up, down, down, and back to where it started. That is what one cycle of sine looks like. But it has been squeezed into half as much distance because of that b value. And again, you have to be careful with one cycle. You got to go slow on that part, make sure that that is as correct as you're going to get it. But then once you have one, you can just copy and paste it a few times until your graph is complete. So by making b equals 2, If we compare these, you can see it just changes how often the pattern repeats. It takes less time because b was 2. And I knew that the period needed to be pi because of the formula 2 pi divided by b. Okay, so this pattern for cosine, the down, down, up, and back to where it started, is still going to be the pattern for cosine in question 10, but now b is not 1, so now the period is not 2 pi. We'll actually have to compute it. Do 2 pi divided by b. b is a half. Dividing by half is the same as multiplying by 2. So this one should have a period of 4 pi. That means I should have to look at 4 pi of horizontal space before I see one full cycle of cosine. Okay, so should look like this one looks like this. Based on how far the graph is, it's a little harder to understand why this one looks the way it does. Back in my, you don't have to write this part down, but back in my head, I'm actually plugging in a couple values like 0. Cosine of 0 is still 1. That's how I knew it had to hit here. And then this is the full pattern. If you started here, you go up, up, down, down, and then you're back to where you started. So now, from negative 2 pi to positive 2 pi, now the distance I'm having to look at to see the full cycle is 4 pi. And that's what happens when you change b to be a half. Okay, so before I give you a chance to ask questions about period and then we move on, what you have to learn, and we're gonna practice this for a few classes, but you have to know where b comes from. b is the number multiplied by x. You will have to memorize this formula for computing period. It's 2 pi divided by b, and you need to know what period means, the amount of space needed to see one full cycle. Okay, so other than that short introduction, any immediate questions about period before we move on to amplitude? Is that a question?
Yep.
Okay, what you got?
Can tangent have a graph?
It does, but we do that in 4.6. We will ask you to memorize what the tangent graph looks like. You can kind of figure out some of it by just plugging in unit circle values like I did on questions 1 and 2. And we will ask you to know things like its domain and range and stuff. But that's section 4.6, so that's for a later day. This section we're only focused on sine and cosine and all the transformations you can make with it. Okay, then a second way to change the graph is something called amplitude. Amplitude, the short version of that would be how tall the waves are. If you want the waves to be taller or shorter, that would refer to amplitude. The definition is that it is half keyword, half the distance between the min and max values of the graph. So if you have a graph, you could take the max value, find the distance from it to the min value, and divide it in half. But when you have a function, you're going to have to know this formula. It's the absolute value of a, where a is the number being multiplied by the trig value. The coefficient of the trig value is a. So let's answer question 13 first, but I'm going to scroll up to look at our graphs up here. The sine graph has a max of 1 and a min of negative 1. So the distance between min and max is 2, but amplitude is half of that. So from a graph you can measure it, or it's the absolute value of the number being multiplied by the trig function. Since there's not a number out there, it's an assumed 1. Absolute value of 1 is 1. Same thing over here. A is 1, so the amplitude is 1. Visually, that means the distance between the max and the min. If you take that distance and half it, you get the same value. So, looking at questions 12 and 13, doing 13 first. Again, A is 1, absolute value of A is 1. On the cosine graph, A is 1, so the absolute value of A is 1. But in question 12, A is 3, which is going to make the amplitude be what?
3.
Okay, and in second part of 12, A is negative 4. So what's the amplitude of that going to be?
4.
Very good. Not negative 4, absolute value of it. Now, that negative still comes into play, but just so you guys know, that negative will be similar to what you did in algebra class. If you know what x squared looked like, what happens if you multiplied it by a negative?
Yeah.
Right, it flips over the x-axis. So this graph, even though I don't think I'm graphing this one, would look like the sine graph, but the wave is going to be 4 times higher. It's going to go as high as 4 and as low as negative 4, but then also you would have to flip it over the x-axis because of that negative. Okay, so for us to graph a couple of these, what we can do is number 14, let's just lightly sketch in what sine looks like. This is just, in red, is regular old sine. And if I throw a 2 in front of it, I'm just making all the y values 2 times bigger. So all the values of 1, you multiply those by 2 and they become 2. All the values of negative 1 get multiplied by 2 and you get negative 2. And all the values of 0 get multiplied by 2, but 0 times anything is still 0. So you can make those point changes, reconnect, and that is what 2 times sine of x looks like. Increases the wave height. Now half the distance between min and max is 2. Whereas if we're talking about sine, half the distance between min and max is 1. Okay, so you don't have to put more than one graph on here, but make sure that if you do have more than one graph on this graph, that you label which one is your answer. Don't leave 2 answers there. At least put f of x next to the one that's supposed to be f of x. Okay, in question 15, I'm going to do 3 graphs. I'm going to just quickly sketch in cosine. So after you get some time to practice this, you'll have it memorized. And you'll say, okay, cosine in red looks like that. If I just thought about the 3 cosine x, that's going to multiply all the values by 3. So all the 1s become 3, all the negative ones become negative 3, and all the zeros stay 0. And then when you reconnect them, if you think about the definition of amplitude, now the distance between min and max is 6, but the definition of amplitude says that half of that makes up the amplitude. So that matches up with 3. And then I'm going to erase my old cosine graph. I don't need it anymore. But to graph this full thing, it's going to look exactly the same, but that negative is going to flip it over the x-axis, just like I talked about with x squared. So this gets flipped over, this gets flipped over, flip over the x-axis, flip over the x-axis, flip over the x-axis. Anything that was on the x-axis is still on the x-axis. Reconnect those, and that's what they were asking us to graph. And again, I'm just going to erase my old work so that there's no confusion. But knowing what cosine looks like, you could then make it look like 3 cosine, and then you can flip it over to make it negative 3 cosine. But that's what happens when you change the a value. You're going to change the amplitude. So far we've seen 2 formulas. Period is 2 pi divided by b, where b is the coefficient of x, And then the second one is amplitude. Amplitude is the absolute value of A, where A is the number being multiplied by your trig function. Okay, so before we move on to the third one, really the last of the, I don't really consider the last one a big deal. So is there any immediate questions about amplitude before we move on? All right, then the next thing would be, what if we want to shift the graph left or right? That is what's called phase shift. So once again, it's helpful to know what sine and cosine look like, just so we don't have to keep flipping our paper back and forth. Just quickly sketch it at the top of your page. Once you know what those graphs look like, then you don't have to talk about that so much. But if I don't want to just make it more or less frequent, period, if I don't just want to make the waves taller or shorter, amplitude, but if I want to shift the whole graph left or right, that's referred to as phase shift. And this has a formula as well. This one is C divided by B, where B is still the coefficient of X. It's the same B that we use to compute period. And C is the number that we add or subtract to X. So if we add or subtract something to X, we are going to be shifting our graph right or left. Now, the direction can be kind of counterintuitive, but it is consistent with other algebra stuff that you guys have done. If this is what x squared looks like, what happens if you make it x minus 2 squared? What did that minus 2 do?
That's the right to.
Right. Usually when you think subtract, you think to the left because of like number lines and such. But if you subtract from x, it goes to the right. And if you add to x, it goes to the left. So it's consistent with other algebra stuff, but maybe not intuitive. Bless you. Okay, so now let's look at a couple graphs that are going to have a phase shift. How we're going to measure them from the function and how we're going to make those changes on a graph. Now, to be fair, the first couple parts of these questions don't have anything to do with phase shift. To graph this, you would have to know what sine looks like. Again, once you have time to memorize that, that should take you about 5 seconds. Because there is a b value that's not 1, that's going to change the period. So I'm going to try not to go too fast here, but my focus isn't period. We've already talked about period, but period is 2 pi divided by b. So if b is 2, the period of this graph should be pi. So I should squeeze the same pattern in to half as much space. And I don't need the parent function anymore. Again, you'll have to excuse me that I'm going quickly on that part, but I'm trying to just get to the phase shift part. Period part is one of the harder ones, but you kind of have to practice through that. Okay, now, because there's a c value, this is where it's going to shift it right or left some. Because this is a plus, that means it's going to go which direction? Left. How much it goes to the left is not just c, it's c divided by b. So in this case, pi over 2. Now we got to start to pay attention to our x-axis here, because again, these are not in terms of 1, 2, 3, 4 like the y-axis is. They're in terms of pi. All the way to the right is 2 pi, so half of that distance is 1 pi, half of that distance is pi over 2. So I want to go left pi over 2. That's 2 of these tick marks in this question. So I could take this point and go left 2 tick marks, it's off the graph. I could take this point and go left 2, and this point and left 2, and this point left pi over 2, and this point left pi over 2, and this point left pi over 2, and I can just do that to every single point, including these, but they just land on each other. And then when I reconnect these, the difference between my purple graph, which was just sine of 2x, and my red graph, which is supposed to be f of x, is that the whole graph got shifted left 2 blocks, which was left pi over 2. Now again, just to make my graph not look overly confusing, I tend to erase the previous parts, but you don't have to erase. I would always recommend that you just graph really lightly until you get to the end, and then make sure you label what you think the answer is. This is f of x, put f of x next to the one you think is the answer. So if you can measure phase shift and you can graph the rest of it, you just move the points 1 point at a time. Move 1 point this much, and another point this much, and another point this much, and another point this much, until you feel comfortable, and then you can reconnect them. So to say that one more time, question 18. If I had to graph all of this, I would first lightly sketch what cosine looks like. Because b is not 1, the period is not going to be 2 pi. It's going to be pi. If b is 2, then the period is pi. So again, I'm going over this part quickly because that's not the focus of this section. But if I squeeze this pattern into pi units, it's the same pattern. And now I'm going to get rid of my old parent function that's just in the way now. That's what cosine 2x looks like. Okay, and then the part that I'm really interested in is because c is not 0, this is going to be shifted horizontally in some direction. Because of this minus, I know I need to move the whole graph to the right, but how much it goes to the right is c divided by b, where c is the number you're adding or subtracting from x, and b is still the same b from period. So pi over 2 divided in half is going to be pi over 4. So I want to take all these points and move them right pi over 4. Well, how far is pi over 4 in this graph? Yeah, one little tick mark. If 2 tick marks make pi over 2, half of that is pi over 4. So I could take this one, move it right pi over 4, and this point right pi over 4, and this point right pi over 4. Just move them all 1 to the right, because 1 tick mark to the right is pi over 4. It's kind of excessive to do every single point, but it also doesn't take that long. And then reconnect them. And if you can see the previous step still, it's kind of nice because you can visually see that my f of x, the one in black, is all 1 tick mark to the right, which is pi over 4. And then just for simplicity, I get the old one out the way. Okay, so now we're up to 3 formulas. Period is 2 pi divided by b, where b is the coefficient of x. Amplitude is the absolute value of a, where a is the number being multiplied by the trig function. And then phase shift, you have to know why it goes right or left, but how much it goes right or left is c over b. B is still the same b from period, and c is the number being added or subtracted to x. So that's how you can make it move right or left. Okay, and then on to the last one, which I don't really call this another formula, but some books kind of refer to this. I guess in a way you need to be familiar with this. But vertical shift is when you want to move the whole graph up or down. That's the last of our transformations. And if you call it a formula, we refer to it as D, variable D. Where D could be where you add or subtract a number to the parent function. So D could be at the end plus 1, or it could be at the start plus 1. But basically what you're doing is you're making the y value 1 bigger. So if you know what sine looks like, and you realize this plus 1 is a vertical shift up 1, you can just take all the points shift them up 1, reconnect, and you're done. And once again, if you have both on the graph at the same time, it should look like a visual shift up 1. It should make sense. Of course, if it's minus, it's going to make all the y values that much smaller. So to graph cosine x minus 2, I would need to know what cosine looks like. I would need to know that this value of D means the whole graph is being shifted down 2. Every y value is 2 less. So take every point that you're sure is hitting a nice whole number, shift them back down 2, reconnect, and it should look like it has gone down 2 compared to the one before it. So we shift up, down, left, right. We change the frequency, we just call it period, and we change the wave heights, which we call amplitude. Those are all of the transformation changes we'll have to practice. Okay, so now to boil all this up and to see how all this kind of comes together, I think on your last page, isn't this the last page? Number 19. Does this move on to the last page now? Okay. All right, so over time, not by the end of today, but maybe by the end of next class, well, that's tomorrow. By the end of tomorrow, after we practice for a while, you will need to be able to graph something like that. This is on the harder end because it's got a little bit of everything. But before we can even talk about how to graph this, we should be able to measure these things from the function. So, looking at this graph, what do you think the amplitude is going to be? It should be 3. So you need to write on your notes here. I know you have it elsewhere as well, but amplitude is the absolute value of A, and A is the number being multiplied by sine or cosine. Okay, somebody else have a guess for what you think period should be?
2x or 2.
Nope. What's the formula for period?
C over B.
That's phase shift. Phase shift is C over B. Period is 2 pi over B, and B is the number next to x. So what is 2 pi divided by 2? Pi. So once you figure out where B comes from and you memorize the 2 pi over B, that's a really quick question. Okay, phase shift is the one that's C over B, but you also have to know right or left. If you're subtracting from x, it's going to the right, but how much is going to the right? You have to take the C value, the thing being added or subtracted to x, and divide it by B. And pi over 2 divided in half would be pi over 4. If you don't, sometimes that's not so easy to see. Dividing something in half is pretty easy for me to do in my head, but occasionally you might want to write it like this. Dividing by 2 is the same thing as multiplying by a half. So it's pi over 4. And then if you want to call vertical shift a formula, it would just be D, where D is the constant at the front or end of the question. If it's positive, you're going up. If it's negative, you're going down. And whatever D is how much it's going up or down. So before we can move into the graph piece, you guys okay with where all those computations came from? Okay. Now, to graph something like this is why I have so many graphs on this page. You can't, well, with the calculator you could, but we're not going to give you a calculator on this quiz because we're not interested to see that you can just plug it in. But you can't just go straight to this graph and know what this graph's going to look like. So, when we get to that part tomorrow in the book assignment, this is what you'll need to do. You'll need to dig through all of this and realize that sine is the parent function. So start off with the sine graph. I've basically been doing that on previous pages as well. So start off with sine. Then you need to make one of these changes. So I don't know. I'll deal with the 3 first. How is 3 sine x going to look different than 1 sine x?
Stretch.
Okay, so instead of going up to 1, it's going up to 3. Instead of going down to -1, it's being stretched down to -3. And 0 times 3 still stays 0. So there's 3 sine x. So to be able to do that, again, I know you're not going to feel like you have mastered this type of question by the time I'm done with it. But you have to understand what this 3 changes, amplitude, what amplitude looks like visually so that you can make that change. But now that I know what 3 sine x looks like, I can deal with one of the other changes. So instead of just doing 3 sine x, let's do 3 sine of 2x. And I'm working off of this now. So this guy has a period of 2 pi to see 1 full cycle. But now that b is not 1, the period is going to be pi. That's what we measured a minute ago. So I need the same pattern to now squeeze into half as much space. I'm still going to let the amplitude be 3, so I don't have to redo that. But now, I want the sine pattern with an amplitude of 3 to fit in pi amount of space. I like to start off at 0 because if I want the period to be pi, I just go to pi if I start at 0. That's 1 full cycle. I feel confident about that. Now I can just copy and paste it a few times until my graph is full. That's what 3 sine x, 3 times sine of 2x looks like. Now that I have this down as a guide, I can make one more change. So I'm just trying to peel this away one layer at a time. So now I will deal with this minus pi over 2. So now I just introduced a c variable. Now that c is not 0, this thing's going to shift right or left some. So otherwise it should look exactly the same as this graph because they're the same function. But now I need to move it right. And how much right is c divided by b? So pi over 4. Pi over 4 ends up being 1 block. I know that because 2 blocks is pi over 2 and half of that is pi over 4. So I could take 1 point over here, move it right pi over 4 and replot it. Take another point on this one, move it right pi over 4 and replot it. Take a third point, right pi over 4, another point, right pi over 4. And you can do that for every one of the points if you want to. But honestly, once you really get one cycle in, it's really just a copy and paste job. So it's going to continue along the same pattern. I think in the textbook assignment and on our quizzes, we always require you do at least 2 full periods, but you'll see why when we move on to the next handout, why you just want to fill out your graph either way. So I have taken what I've memorized about the sine graph. Then in step 2, I changed the amplitude to 3 because A was 3. Then I changed the period to pi because B was 2. And then most recently, I moved everything right pi over 4 because C was pi over 2 and B was 2. And then the last step, the easiest one, is if I now know what 3 sine of 2x minus pi over 2 looks like, what's the last part? Is it plus 1 or plus 2? Plus 1?
Plus 1.
Okay, what's that going to do to my graph? Okay, so every one of these points just goes up 1. This one moves to here. This moves up 1. This moves up 1. You can move every single point up 1 if that makes you feel more comfortable. But once again, once you really have one full cycle in, carefully, then you can just repeat it until your graph is full. So again, this one's on the harder end. Not all of the questions you will have to graph will be that difficult. But I needed you to see the process. You got to start off basic, sine, make one change like amplitude, then make another change like period, then make another change like phase shift, and then if there's still another change to be made, then make it, in this case, vertical shift. If you do it one step at a time, you know how to measure all those things, and you know what sine starts off with, then you can do that with some practice. Okay, I didn't think to tell my other classes this, but let me just go ahead and say this real quick, because I think sometimes this will help you in the future. Let's say that we ask you on the quiz and the test to graph this, and you graph it, you think it's okay, you've checked it the best that you can. Just so you know, just like I made a table on our first page with some easy values, I could do the same thing here. So does everyone agree that my graph looks like it's going through 0, -2? That means if I plug 0 into this function, it better come out to be -2. Otherwise, I know my graph is wrong. So imagine plugging in 0 here. This goes to 0. You get sine of -pi/2 plus 1. And what is the sine value at -pi/2? This is unit circle. Where's -pi/2?
-90 degrees.
Okay. What's the y value there?
0, -1.
What's the y value?
Oh, -1.
Because that's all I care about. And -3 plus 1 is -2. So that doesn't guarantee that your graph is right, but if by plugging in 0 and solving for y equals -2, if 0, -2 is not on my graph, then I know I did something wrong. So that's a way that you can feel a little bit better about those graphs. Okay, last thing before I give you the directions for our other handout today, and then you'll have the rest of class to practice and play with that. Actually, there's one other thing I want to show you, but that's okay. This is a pretty common math trivia type question. What would be another equation that would look like the sine graph? What's another way to graph that without using sine? Okay, I heard something about cosine. Cosine doesn't look the same as sine, but it might if you did what to it? Moved it to the, you said to the left. Okay, so technically, you can move it right or left. It just depends on how much you're willing to move it right or left. So notice cosine, if I look back at page 1, if I take like this point on cosine, I could either move it this much to the right, which would land here and be consistent with the sine graph, and that would be right pi over 2, right pi over 2, or if you'd rather go left, you could. It's just that to go left, if I took this point and tried to match it up to this point, I would need it to go this distance. So if you go left, you would have to go left 3 pi over 2. So you can move it right or left, but the distance you would have to move it depends on which direction you go. But sine and cosine graphs look the same. If you're willing to shift cosine left or right some, you could make it be a cosine graph. If you're willing to take sine and shift it left or right some, you could make it be a cosine graph. So I say that because this last handout for today, this is where you guys are going to kind of play around with these and try in your calculator to come up with an equation that matches that. But question 1 here, this could be a sine graph or a cosine graph. Both of them can be correct. One of them probably needs less of a phase shift, which makes it a little bit easier. But we're going to do a little bit of guess and check here. So on question 1, just out of curiosity, does this look more like a sine graph or a cosine graph to y'all? Okay, I'm hearing more cosines. Again, sine is not wrong, but it might be a little bit more work. Okay, so cosine looks like this. I'm just kind of sketching it in to show what mentally I'm thinking about. So what's one thing that's different about this graph? Okay, stretched which direction? Okay, vertically. And so if the one I'm trying to create is taller than this one, that means I need to change what about my graph? What's the vocab term?
Amplitude.
That is amplitude. Good. And what part of the equation affects amplitude?
The very beginning of cosine.
Good. So the A value. Then with the definition of amplitude, it's half the distance between min and max. Looks like the distance between min and max is 4. So amplitude would be 2. Now, amplitude's 2, but A could be positive 2 or negative 2, whatever you think is easier. You never have to reflect it over the x-axis if you don't want to, but you might have to do a phase shift then. It might be in difference. Okay, the other thing was, let me put this back real quick. Actually, I will update it with our amplitude. The other thing that looks off is the frequency, which we call period. What part of the equation changes period?
B.
Okay, B, which is right next to x. And for me to know what the period should be, I have to measure it from my graph. So you're going to have to know that period is the distance to see one full cycle. Now we're about to talk about this in the calculator in just a second. But this is 0. The far right we want to be 2 pi, and the far left we want to be negative 2 pi. So if all the way over is 2 pi, this is 1 pi. So to see one cycle, it looks like it has a period of pi. And if the formula for period of pi is 2 pi over b, and I want it to be pi, what does that mean b needs to be?
2.
Okay, plug in 2. Now, regardless if I pick sine or cosine, the amplitude is 2 either way. Regardless if I pick sine or cosine, b has to be 2 to give me a period of pi. Now, depending on if I want to make that 2 negative and flip it, or if I want to use sine, I might have to also shift left, right, up, or down some. I'm going to say that we probably don't need to shift up or down any, because to me it looks like there's just as much graph above as below the x-axis. But this is where there's a little bit of guess and check involved. So with the calculator, we're going to graph this. And if it looks exactly the same, then this is one of the answers. I can't just share the answers with you guys, because again, every one of these could have 10 different answers. But to graph this in your calculator, you've probably never had to do this before. So in your calculator, you will need to be in radian mode. Sometimes if you forget, your calculator tries to adjust, but you really need to be in radian mode. Go to y equals type in what you think the function is. So we talked about the amplitude needs to be 2. Most people said it's more like a cosine graph. We said the period has to be pi, which means b needs to be 2. And that's all we talked about. Now, chances are, when you hit graph, it's going to look something like this. The problem is, this is the standard -10 to 10, -10 to 10. That's not how our graphs are set up. One thing that you can do is you can hit zoom 7 for zoom trig, and it tries to change it to a standard trig setting. But a few years back, they added this, and I don't know why they did this, but if you go, this is actually 2 pi, and for some reason they updated it to where zoom trig shows a little bit to the right of 2 pi. So if mentally you can block this out, and this is -2 pi, if you want to mentally block this out, then you can see if that matches up with your graph. I don't like to do that. So I take it a step further, and I hit the window button. And if you notice on this worksheet at the top, it has the units. I wanted to go as far left as -2 pi, so I put that in for my x-min. I wanted to go as far right as +2 pi, so I make that my max. And just to make it look exactly the same, I want to change y-min and y-max as well. Go down to -3 and up to +3. If you make those changes, your graph should look not close, but identical to what's on the paper to know that it's correct. Now, I can't flip back and forth like you guys can, but that doesn't look like our number 1, does it?
No.
And that's okay, because we're practicing this. We graph what we thought the answer might look like. We got to think about what's different to think about what needs to change. Does the amplitude look okay?
Yes.
All right. Does the period look okay? Is it repeating at the right rate? Okay, so probably don't want to change those. If I remember right, I think there's like a point right here on your paper. Is that true? And there's a point right here. So if you wanted to, you could shift it this much to the right, so you could subtract from x. But if you want it to go right pi/2, your c divided by b has to equal pi/2. If you want it to go this way, you could make it go left by adding to x. But to make it go that much, that would be pi/2. So you would have to make sure that your c divided by b comes out to be pi/2. Or, what would be an easier fix?
Minus it.
All right, and again, this is optional, because if you would rather shift it right or left, you can. But on this one, if we just flip the whole graph over the x-axis, we make a be negative. That doesn't mess up the amplitude, because amplitude is the absolute value. But it does reflect the graph. And now, do you see how it looks exactly the same? Not close, but exactly. Then that is an acceptable answer. You could write that down, circle it, and move on. You don't need to find multiple answers. Now, if you thought that looked more like a sign graph, you're welcome to go for it. I just think that it would be a little bit more work. You probably would have to shift it right or left a little bit. And that's usually the hardest part. Okay, let's look at one more together. And then again, really the idea to this is you make a guess about what you think is supposed to happen. You graph it in your calculator. If it helps, you keep the change. If it doesn't help, you try something different. And through that back and forth, you kind of figure out how A, B, C, and D impact what your graph is going to do. Okay, so one last one as a group. Number 2, does this look more like sine or cosine to y'all? Okay, I would agree. If it goes through the origin like that, it's probably sine. But just to be clear, cosine is perfectly fine. It's just that cosine is going to be more work. Well, the sine graph, I'm visualizing the sine graph in my head to think about what's different. But you might want to sketch it in. Right now, this is just sine in red. It looks like the amplitude should be smaller. So what should I try to change about my equation? Okay, put 1/2 in for what?
A.
Okay, let's try A to be a half. I think that what that's going to do, and as you do a few of these, you should be making more and more better educated guesses. But if you make A a half, now it only goes up to a half and down to negative a half. So I think that's what 1/2 sine of x looks like. But that's still not exactly the same. We got to change something else too. Looks like it needs to repeat more often, so I need to change the period. The way we're going to change period is by putting a number in for b. Now, you're welcome to guess and check that away, but at some point you're going to want to be a little bit more efficient. So, to know what the period's supposed to be, pick a starting point and an ending point of one cycle, and this is obviously 0. What is this? What x value is this? The x-axis is not in terms of 1, 2, 3, 4.
So pi.
It's pi. If this is 2 pi all the way to the right, halfway is 1 pi. So to see one full cycle is pi, and the formula for period, this is so you're doing less guess and check, is 2 pi divided by b. So what is b going to need to be to give me the period that I want? 2. So throw a 2 next to x. Throw that in your calculator. If it doesn't look right, what doesn't look right hopefully gives us a hint about what to change. And if it looks exactly the same, which I think this one does, then that is an acceptable answer. You can circle it and move on to a different one. So again, it's a lot of guessing at first, but then you start to make some better, more educated guesses as you go along. The last thing I want to show you guys before I let you work at your pace the rest of class, if this helps, on our class website, okay. All right, we'll go ahead and try the next one. My computer is. Give me just a second to pull this up. This will not help with this assignment, but on our class website here, under number 24, I did put together, well, I stole some of the work, but I put together 2 Desmos slides. If you want to click that, One of them is for graphing sine and one is for graphing cosine. And so on the left here, you can see that it's graphing a sine bx minus c plus d. So they're showing you where a, b, c, and d are. And it's got little sliders. So if I make this a value bigger, what's it going to do to the graph?
Get up and down, bigger. Stretch.
You see how that changes it? Or if it's less, it flips it and makes it. So it lets you kind of play what happens as A changes, what part of the graph changes. Or B should affect the period, so you can see it could repeat more often or less often. C is going to shift, do a vertical shift. If there's a C value, and if there's a D value, what would that do to the graph?
Make it go up and down.
Right. The whole thing goes up or down. So again, this doesn't really help with this assignment because B and C are not in terms of pi like we usually do, but it does let you just kind of play with them and helps you understand where A, B, C, and D come from and what happens as you change each one individually. So feel free to click that link if you think that will help you here. But otherwise, I need you guys to try to finish this up today. So go ahead and start with question 3, and I will come around and help in just a minute. And you got about 25 minutes. But again, the first few should be a little bit slower. Also, just so you guys know, most of the time you don't want to be in this trig zoom. So when you need your calculator to go back to the standard -10 to 10, -10 to 10, if you do zoom 6, it puts it back in standard zoom. So that's good to know also when you mess up your graph sometimes and you don't know how to fix it. You can just do zoom 6 and it puts it back to the way you're used to seeing it. Are you on the back?
Oh, I'm just getting which ones I think I can be cool. Okay. Do I need to go in order?
No, that's fine. I didn't know if it was because you didn't know how to start something. I didn't know why you were sticking around. But that's fine. your yeses don't seem to be getting better, something's not clicking, then just call me over as I come around, and I'll try to help you see what thing you're not considering. I would like you to try to finish this up in class, but if you don't, you could take a few minutes into the next class tomorrow.